Okay, hello everybody. My name is Alex Ozun, and Daniel, thanks a lot for this great introduction. I'm incredibly excited to be here. I heard so many good things about this conference. So yeah, let's just jump into it. The topic of today's presentation is how to make invalid states impossible in your apps. And this is something I'm incredibly passionate about, and being part of a huge company like American Express, we have maybe like 60 iOS engineers in the team. Um, Managing invalid and impossible states is a huge part of our kind of engineering culture, and indeed it is part of our onboarding process. So first I want to kind of clarify the kind of vocabulary real quick. I use the word invalid state, but this can be confused with like validation and things like that. What I really mean, like completely legal state. And let me give you a couple of examples just to get everybody on the same page. So here's a couple of examples where we have a perfectly legal state. So something like having an email validation form which says, hey, your email format is incorrect. That might be, the email itself might be legal, invalid, I'm sorry, but the app state is perfectly legal. We expect this app state. Same goes to any sort of like network problems or hardware problems, etc. Anything that is part of our applications kind of life cycle is perfectly legal. So what we really are talking about today is illegal app states that perhaps violate our app's logic in some way, or they break our business rules, or they undermine the data integrity, or they introduce some inconsistencies to our app states. And so as an example, suppose we have a taxi hailing app, and we are in the trip is in process, so we are in a taxi, we already in the middle of a journey, and having something like pickup location is not defined, well, that is an illegal state, because this would not allow us to calculate the price for the trip, but also it kind of breaks the rules of taxi business and even just the common sense. Like if I'm already in a taxi, there must be some pickup location. So we should have never started the journey before we registered the pickup location. So this is kind of a quick example. I hope we're all on the same page of like what we're talking about today. And so when it comes to management of illegal states, there really are kind of two broad categories. One is the dynamic approach, and the other one is a static approach. So dynamic approach handles illegal state at runtime, so when our program is already executing, whereas static attempts to do so during the compilation. Dynamic approach attempts to recover our app from the illegal state, or maybe just before it happens to prevent it, or maybe shortly after it happened to kind of recover. Whereas static attempts to completely prevent it from ever happening in the first place. Indeed, the title of this talk says, make them impossible. And how we do this in the dynamic approach? Well, by using control flow operations, so like if, else statements, guards, switches, try-catch blocks, etc. And the static approach attempts to utilize structural and nominal typing, or the type system of our language. And today's talk will be focused on the second, on the static approach. So I like to explain things through examples, so let's jump right into the first example. So we will look at the forgotten password recovery flow. Suppose we're building an app that has a registration form, and this registration form requires a user to provide at least one contact method, either an email or a phone number, or it can be both. But one contact method must be provided. And so this screen handles all the input validation. It makes sure the user has an input. But once we are done, once the user is registered, we expect every registered user to have a contact method. And we can express our contact methods as such. We have email and phone number. They're optional, so we can kind of mix and match them. So let's verify that this data structure satisfies our requirements. So here's the input or state of the user, registered user, which has only an email. This one has only a phone number, and this one has both. So this data structure is flexible enough to satisfy our requirements. Now, sometime later in the in the journey of using the app, the already registered user might forget their password, and we may suggest them, hey, why don't we send you a recovery link to your contact method that you gave us? And so the implementation might look something like this. So we generate the recovery link, then we go and check their records, see, okay, you have both email and phone number, let's send it to both. Whatever is more convenient, you'll pick up. If it's only an email, we send it to your email. And if it's only a phone number, we'll do the phone number. But now, I'm sure most of you have noticed this. When you have this chain of if-else statements, well, the natural question is, well, what goes into the final else? And this is like, this trips me up all the time. Whenever I see like a chain of else if statements without else, I'm like, dude, where's the else? So what does this else statement represent even? Well, it represents an illegal state because it means that the registered user somehow doesn't have any contact details. And this is a huge violation of the rules of how our app works. We can say that the user's record is corrupt, essentially. So what do we do in this case? Well, we can be like, we are UI developers, right? Like, we'd be like, sure, let's show some very useful error message. And we do so saying, hey, call Alex on a tech support, this number. So here's the problem. The user makes a call, and this is me, L1, a perfect representation. So the user explains the problem, and usually this triggers a chain of events. And I don't know how many of you work in large corporations. This can take weeks, months even, to reach the final developer that kind of has access to database that can go and rectify this error. And indeed, usually these developers have an army of managers that fight for their time. So the problem might never be solved at all. Now, what we can do instead is we can crash the app, saying, hey, this state is illegal. We can also add like a user ID for investigation. And this is definitely better because then these errors would be reported often directly to responsible engineers that monitor these error reporting systems. So this is definitely better. But from my experience, teams usually are quite risk averse, and they won't be willing to crash their app like this. So oftentimes they will just silently log an error, like, okay, for future investigation. But obviously we need to figure out the root cause, like why this happens in the first place. And the reason is, of course, because our data structure was a bit too flexible. It allowed one more state, which represents a completely illegal state. And so here's a philosophical question. How do you make a statue of an elephant? Well, you take the biggest granite block you can find, and you chip away everything that doesn't look like an elephant. So obviously, our contact details sculpture doesn't look quite like the one we want. So we need to figure out what to chip away. And the answer is actually not obvious, because, well, we can't remove any of the fields without restricting the model too much. And we can't even make any of them non-optional. If I make email non-optional, then it would mean that email is required, but it's not what requirements say. So let's break it up, and let's refactor this data structure in a way that would allow us to eliminate the illegal state. So first, let's desugar optional type. Optional type is a generic type, which is an enum, which has two cases. All of you know this very well. So let's specialize this optional without two types. So pretend we have two specific enums, optional email and optional phone number. So we have two enums, and we combine them together under one struct. So what this means, it means that we have a permutation of all their cases. So we have some email and some phone number. some email and no phone number, no email and some phone number, and none, none. And so if we merge them in a single enum, we get something like this. And notice how these 4 cases exactly match the 4 states that we just observed. And if you look at these 2 data structures, this is incredibly interesting because both of them contain the exact same data. It's exact same data, just in a different shape, in different representation. These data types are equivalent. Or if you want to impress your colleague, you can say they're isomorphic, which means we can transition from one representation to another without losing any data. So, but the second representation at the bottom lays out state in a more obvious way. And here we can actually easily answer which part of the elephant we need to chip away. And this is this part. So with this refactored data structure, we can go back to our function and update it. And what we see here is that the illegal state is not even there. It is statically guaranteed that we will never face the illegal state. And I must add real quick that, again, the validation that the user provided the input contact details happened during the registration. At this point, we shouldn't worry about this. We should treat this as a invariant of our application. And so, paraphrasing Antoine de Saint-Exupéry, in state modeling, perfection is achieved not when there is nothing more to add, but when there is nothing left to take away. And so, if we look at this problem schematically, we had a set of legal states and a set of possible states, and the set of possible states was larger. And in this difference laid our legal states. And so what we did is we matched these sets. And look, sometimes it's impractical to always model our state in a way that only permits legal states. Sometimes you will have to make compromises, maybe for convenience, and we'll handle these in legal states dynamically. That's fine. What is not fine is to go from version 1 to version 2, where we have a bit more legal states, but then the legal states grows, and then it grows even more, and you don't control this difference. So what I want you to take from this is, anytime your requirements change and your application states becomes more complex, which is inevitable, go back to the drawing board and reconsider and do changes intentionally, perhaps refactoring your data type. Don't just add more stuff, add, because this will result in this. All right, so let's take a minute to talk about algebraic data types. This is a scary sounding concept, but it's an incredibly simple one, but also a very powerful one that will help you solidify what we just did. So algebraic, you can think about data types as just sets of possible values. So Boolean is a set of two possible values, true and false. And uint8 is a set of 256 values from 0 to 55. And in Swift, we have two interesting types, structs and enums. So enums represent a sum of data types. So we combine Boolean and number as a sum of their values. So we have two possible Boolean cases, and then 256 number cases. So in total, we have 2 plus, you see, 258. So it's easy to see how it's a sum type. In contrast, structs, they combine these values. They do perform permutation. So we have Boolean true and false for all zeros, then true false for 1, etc., until the 26. So it's a multiplication of types. Anyway, this is fun, but it's really just kind of an interesting abstract thing. What is relevant for our talk is the next part, where we can combine enums inside of structs and structs inside of the enums, and how this relates to each other. So you all know this simple formula where we can distribute a multiplication over addition. How we used to call it back in my school in Ukraine, open in parentheses. So simple formula, you all can understand it. Now turns out that exact same relationship happens in Swift types. So A plus B is just an enum, either A or B. C plus D is an enum, either C or D. And so the left-hand side of the formula would be a struct that has these two enums inside, okay? And now, when we multiply types, we just put them in a struct. So it's A and C together. And now, and we can also use just tuples. Tuples and structs, they both are these kind of combinations or product types. And so the right-hand side of the equation would look like this. We have an enum with a bunch of tuples, or a bunch of structs if you prefer to use structs. And the thing is, these two representations are equivalent. So it's exact same data, but in different shapes. That's what you saw in the previous example. But now you can see, hopefully, the actual fundamental relationship, how these types relate. And so here's another very specific and fun example. Going back to our contact details. Suppose we have two types of contacts. One is the text-based, and it could be either a pager or an enum or an email. And we have a voice-based contacts, which is a landline phone and a mobile phone. And we ask user to provide one for each category. So give me one voice-based contact, one text-based contact. So this is our compacted representation. So the expanded representation, we can think about kind of as like a categories. So the user can choose, or we can categorize a user in a funny way. So we can say, if you have landline and a pager, well, sorry, you're a boomer, my friend. Now, if you have a landline and you upgrade it to an email, well, you're probably a Gen Xer. If you have a mobile phone and an email, that's kind of me, then you're a millennial. But if you have a landline and a pager, or I'm sorry, mobile phone and a pager, well, I'm sorry, you're just a weirdo. Like, who does that? And according to terms and conditions of our business, well, I'm sorry, we don't work with weirdos. So this should go away. So again, I just wanted to kind of solidify this relationship and how this expanded form allows us to unveil illegal states. So the problem we faced here is that illegal state is often hidden within the structure of your data types. And the solution is you need to know how to refactor your data types to reveal illegal state. And sometimes you can use those relationships. Let's jump to the next example. Now we will look at how structural typing can help us eliminate illegal states. So suppose we're building this app which has surveys. So we show user a series of questions, and they can go to the next question, back to the previous question, and so on. So like a chain of questions. And so we can represent this using this data structure. We will have an array of questions and a position or pointing at the current question. Now, here's the example of a value. So we have 3 questions, starting from question 0. It's all great. Now, we want to use this data structure on our UI. So we want to paint the current question. So we go and reach out to the questions array using the current position, and we get the current question. Now we are ready to paint this on a screen. But here's the problem. What if we have an empty array of questions? Well, this represents an illegal state, because if you think about it, what's the point of a survey flow that has no questions? It's ridiculous. It doesn't make any sense. If we have no questions, just don't show a survey. So this is an illegal state. But we can go and kind of guard against it by checking if questions is not empty before painting the first question. Okay, so that's good. But what if now we have a position number 42, and question 42 does not exist on a list? That obviously is another illegal state, which means the position is out of bounds. And by the way, notice that the word bounds is outside the bounds of this slide. That's kind of my obsession about details here. So we can guard against this problem as well, and you all probably done this check a million times when working with arrays. We check the lower bound and upper bound. Very good. But then you might think, okay, this data structure is kind of pain in the butt. We need to perform all these checks all the time. How can we save the user from this pain? Well, let's go to object-oriented programming. And if we look at the 4 pillars of object-oriented programming, one of them, and perhaps the most important one, I guess this is subjective, is encapsulation. So we might think, say, okay, let's encapsulate all these checks within that type. So the first thing we do is we make the position private set, also known as look but don't touch. This is a scientific term. So with that, we protect this state. So we encapsulate the access to this state. And so we can create a initializer that guards against empty questions and even sets the initial position to be 0 and not like -1, for example. So this is good. We encapsulated these checks. Then when we go to the next question or to the previous question, we guard bounds, upper and lower bounds. So fantastic. We hidden these checks within our type, and now everything is protected. And we can even go and change this to be a class, to be idiomatic object-oriented programmers, signaling that this is a proper object that manages its own state internally. And this is like a quintessential dynamic approach to managing illegal states. And it's perfectly fine. I'm not criticizing it. But this is a good chance for us to think about, is there a different approach? And indeed there is. So first let's kind of go back and look at these two fields. So if we look at these two fields and try to understand why we're having these problems, why we have to perform all these checks. Well, the reason is because these two fields represent completely detached, disjoint, disconnected sources of truth. One is for the list of questions, and the other one is for the position, but these are completely disconnected. And every time we perform these checks, we essentially mentally trying to reconnect these disjoint sources of truth. And so this is a good moment to talk about nominal and structural typing. So first, nominal typing. You all are intimately familiar with nominal typing because it's the type system that Swift uses, which relies on type names. So we have a cat and dog, which have identical structure, but they're two different types. And if we have a function that takes a dog, we pass it a dog, it works, but if we pass a cat, it won't compile. This is all expected, and it's fantastic. We have a great safety to prevent mixing cats and dogs. And so if we look at the structural typing represented by Python here, so equivalent code in Python, we pass a dog, it works, and we pass a cat, it also works. Well, because Python's type system is a structural typing system. So this method, praise a dog, all it cares about is that it has a name field. It cares only about its structure. And indeed, dog is just a label. We can say has name, which is more kind of, explanatory. And you might think like, okay, structural typing sucks. It's like it's a huge step back from the safety we get with nominal typing. But here's an interesting thought. As a idiomatic and thoughtful structural typing programmer, in Python, you are really forced to think really hard about the structure of your data to ensure correctness and safety. And so as Swift programmers, we can learn from that. So here's a question. How can we represent these checks in the structure of a data type itself? So the first one is empty, it's easy. All we need to do is add the first question, and this first question is an invariant, or guarantee that there will always be a first question no matter what, which means there will be a non-empty list of surveys. The second problem is position is still detached. So how can we reconcile these two sources of truth? And the way you do this normally is you have a single source of truth and you compute the rest of the state from a single source of truth. So let's see if we can somehow compute the position from data itself. And we can do that by introducing another list. So now we have a list of all the previous questions, the current question, and list of next questions. And the position would be just a count of previous questions. And here's an example you will see clearly how it looks like. So this is the minimum possible survey. We have a single question, and it's a current question, and you must have this question. And the position is 0 because the previous array has 0 elements. But let's look at a few more questions. And this visualization, I think, helps to understand how this data structure works. So we start at the question 1, and we have a couple more questions. When we move to the next question, it cycles through them like this. And if we go back, it cycles like this. So the data structure itself captures both the state of the traversal through survey questions, as well as the guarantees that there is at least one question. And so if we look at our previous illegal states, it is not possible to have no questions, and it is not possible to go out of bounds because the questions themselves, we don't have a separate tracker. So no illegal states possible here. And so the implementation of go forward function would look something like this. We take the first question from the next questions array. We make it the current question. We drop this first question from the next array. And we put the previously current question to the previous array. And now at this point you might think, okay, but what have we achieved here? We still have this go forward method. We still sort of have encapsulation. So what's the gain? So let's compare it to the initial example. The difference is subtle, but incredibly profound. So before, and also note that the top function kind of looks more elegant, it's shorter, but the first function, the first example, used this method to guard fragile data integrity. It encapsulated those checks, whereas the second one simply offers common functionality. And let me prove it to you. Pretend we are library designers that build this survey data structure. In the second iteration, I could simply ship just a survey data structure and nothing else, no functionality whatsoever. And I will be 100% confident that users will not be able to break this data structure. It is impossible to make a legal state of the survey. And so I can simply say, hey, app developer, go and build your own go forward function. You might make a mistake there from logical standpoint, going maybe to incorrect question, but you will never be able to create an illegal or inconsistent survey. In contrast, or let's pretend they want also to build some really fancy edge case scenario. Maybe they want to jump to a random question. Again, they can go and just build this. Implementation doesn't matter, but they can just go and shuffle questions in the way they want and produce a new structure. In contrast, the original implementation, if we try to extend this library with our own function, well, this wouldn't work because it won't compile, because the position is hidden from us. We cannot edit it. And that is because the library developer relies on encapsulation as a mean to protect data integrity. So they cannot afford to share data structure to us or allow us to extend its functionality. So as app developers, we have no choice but to rely on library developer to someday implement this method for us. If I had to this is just I don't literally mean that it uses security by obscurity, but it's kind of a good analogy. It's sort of like it obscures the details from us. Whereas this one has security by design. And so the survey data structure itself is actually a pretty common generic structure known as zipper, because it kind of zips through elements. And you can find it in standard libraries or languages like Haskell or Elm, languages that essentially care a lot about correctness. And so the problem we saw here is state fragmentation and internal inconsistencies that were allowed within our data structure. And then we solved it by defragmenting our state and deriving a state from single source of truth. I will close with this one final example. And this is from a standard app Swift library. So let's pretend we are building our own UUID type. And UUID is just a string of random characters formatted like this. And so the first thought, naive thought, will be like, oh, it's a string, so let's just say type alias UUID is string. Well, we can all agree that it's a horrible idea because now we can accidentally mix a string saying hello Alex with like a proper UUID string. It's a bad idea. So the next step is let's introduce a new named type, a new nominal type called UUID that wraps UUID string. And so when we initialize it, we again generate this random string at the top and put it into a UUID string. So this is better because now we can't mix UUID string with just any random string. So we have reclaimed nominal typing. But let's take one more step forward. UUID isn't just a string. It's a well-defined string of 16 byte. It's a 16-byte string. So a byte is a uint8. We can represent it like so. So we need 16 of those. So we can go ahead and put 16 bytes into our type like this. Well, we don't really need like individual fields for each. We can have just a single tuple of 16 elements. So now we have 16 bytes in here. And we make our UUID string computed from it. So it takes those actual raw bytes and formats them in a string like that at the top. And so our initializer will generate 16 random bytes. And this is much better because it has both nominal typing as well as structural typing and internal structural integrity. And if you look at the UUID implementation in Swift Foundation, which is open source, you will see that this is exactly how it is implemented. So wrapping up, use algebraic data types, enums, and structs to model complex state. And make your state explicit and intentional. Every time you need to add new state, go back to the drawing board and reconsider. Does the current structure form still satisfies your requirements, or do you need to refactor it? Understand how to refactor data types to reveal and eliminate illegal states. And use structural typing as well as nominal typing to encode rules into an invariance within the structure of your data types themselves. So that is all. You can scan this QR code if you want, and it will give you some links to my social media and blog. I've written an article on this very topic, and it has many more examples. We haven't covered everything. There's so many more techniques. So go ahead and read that. Yeah, that's all. Questions? I think I'm good to go to questions.